Do it tomorrow. All right, so just a little reminder about what's coming up this rest of this week. So I believe today's Wednesday. So we're going to finish off section 3 today, and then Thursday and Friday we are going to do section 4. I was already jumping ahead to next week. Because next week, I am going to try to see what I can do in terms of small experiments. Okay, those that are at home are just going to have to be excused from it. But I have a series of small scale experiments for Newton's laws that I like to do, but I don't know. I don't know what to do because I don't want to give people into close contact if we don't have to, especially with the holidays coming up. So I don't know. There was one especially that I'm not going to do. That was one where we had to take. It's actually a fun one too. Strung a string all the way across the room, and then we had a balloon with a straw attached to it, and we were doing Newton's rockets, basically applying Newton's laws about equal and opposite, and how it can propel objects forward, like we see in jets and everything like that. But how do balloons go? How do you make balloons fly? Air. Where does the air come from? Yeah. You see the problem there? I don't know if we want people's air kind of just getting all the way across the room. So that one's already off the table. But again, I don't know what to do. So I will try to figure that out shortly, let you know, because that's going to determine when we're going to have the test. And of course, if we don't do the labs, then the test falls at a weird time where we still have some days before Thanksgiving. And I don't like to do stuff with like 2 or 3 days before we're not going to be here. So I don't know. We'll figure it out. Okay. But what I do know is we can at least get through the rest of chapter 4's material. Okay. So again, if you don't have your notes out, you want your calculators out too. And we will be using our book. So I'm looking over in that direction. Aha! Aha! Because I think that would just be an amazing way to end or to leave for Thanksgiving break if someone decided that they wanted to take the turn and sing. So, anyway. Hello to everybody at home. And you're also going to have to wait to the end of the video to figure out what your homework questions are going to be. So, or I might put it in the middle or some other random time. You're just going to have to watch. Don't worry about me. All right. So, we are talking Newton's second and third laws. Okay? One of his laws gives us probably one of the more famous and most used equation that we like to utilize in physics. Okay? We're going to talk about that. That's going to be your new formula once we get there. Okay? Today's discussion, we are going to describe an object's acceleration in terms of its mass and the net force acting on it. So right there, that first little bullet point, talking about Newton's law and the famous formula. We will predict the direction and magnitude of an acceleration caused by a known net force and identify action-reaction pairs. Okay, we only spend a brief moment on that. Action-reaction pairs. In intro, I know we covered that a little more in depth, okay? But it is a kind of a weird concept. It's a very weird concept to think about, okay? Because when we have action-reaction pairs and Newton's third law, you would think that nothing could be accomplished in this world, okay? And we'll talk about that here in a moment. All right, so your new formula is Newton's second law. If you want to write this down, you can. You don't have to. It's a very simple, very known formula. What his second law states is that acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the object's mass. So, basically, if an object is larger in mass, what's it going to do to its acceleration? Decreases. Again, the larger the mass, the slower the acceleration. Okay? Think about a sports car versus a truck, a semi truck. Okay? Who's got the larger mass? Semi truck. Therefore, who would we expect to have a faster acceleration? Sports car. Okay? So, we get the formula of F equals m times a, but we also have the summation symbol there. So we're taking all the forces into consideration when we are talking about Newton's second law. From intro, we didn't have that summation designation there. But now we're taking into consideration all of those. Okay? So we're going to go ahead and toss in this video of Newton's second law of motion and its applications or observations in the NFL.
To be an NFL kicker takes more than just nerves of steel and a strong leg. It also requires help from one of the key laws of physics.
It's easy to say, well, I just kicked the ball. Well, let's delve into it. Let's look at the specifics. What actually happens when you kick the ball, and why does the ball go where you ask it to go? And it is Newton's second law of motion.
The second law is one of three laws described in 1687 by Sir Isaac Newton, who used them to describe how and why objects move.
So the second law says if you have an object with a mass that is accelerating, and acceleration means a change in velocity, that is equal to the amount of force applied to the object. The way we say it with words is F is equal to ma.
This also means that in order for an object like a football to accelerate, a force must be applied. To illustrate Newton's second law in kicking, we asked Morten Andersen, the NFL's all-time scoring leader, to perform his craft in front of a high-speed phantom camera. The entire procedure unfolds in less than a second and a half, from snap to hold to kick.
It's all about training and rehearsing and doing something over and over and over again.
To reduce the chance of a block, NFL kickers take just 3 steps to the ball. The final step is with the plant foot, which provides the stable platform for the kick.
I call it the moment of truth. And the moment of truth is basically when your plant foot hits the ground next to the ball. You're either in the right position or the wrong position.
The kick itself involves the entire leg building the force necessary to launch the football.
It's a hammer, and you're swinging the hammer, and you're trusting it, and it's going to be, impacting the ball with great velocity.
An NFL kicker's foot is in contact with the ball for just 8/1000ths of a second, and in that time, his foot applies up to a ton of force to the ball. This quick, violent strike is a perfect example of what's known in physics as an impulse.
Impulse is an important concept because there is a finite time over which the foot is in contact with the ball, and during that time there's a force applied to the football.
An impulse is equal to the force multiplied by the time the force is applied, represented by delta T. If force is graphed versus time, it's possible to see how a larger force or a longer time for the force supplies a bigger impulse.
Since impulse is really just the change in momentum, and since the ball doesn't change its mass, we're really just talking about the change in the speed. The bigger the impulse, the bigger the change in speed, which means the faster the ball is moving after it leaves the kicker's foot.
Ironically, Andersen says the distance of the field goal doesn't change his approach to the kick itself.
Eventually, you want to look at a 50-plus yarder, like a 40-some yarder with some room to spare. I think that's a good way to kind of fool yourself into thinking it's a shorter kick.
Whether the kick is short or long, Newton's second law explains what an NFL kicker must do to send a football through the uprights.
So, Newton's everywhere, even in football. So, third law states if two objects interact, the magnitude of the force exerted on object 1 by object 2 will be equal to the magnitude of the force simultaneously exerted on object 2 by object 1. And these two forces are opposite direction. So this is a little easier, a little cleaner when you say for every action there's an equal and opposite reaction. Okay? This is where the idea of action-reaction forces come into play. Okay? If we have two objects interacting, they're going to be interacting equally and in opposite directions. Now, think about an action-reaction force here. Okay? They do not imply that the net force on either object is 0. They are equal and opposite, but they may still have a net force. Okay, so consider driving a nail into wood with a hammer. The force that the nail exerts on the hammer is equal and opposite to the force that the hammer exerts on the nail. But there is a net force acting on the nail, which drives the nail into the wood. How is that possible? If the nail and the hammer exert an equally opposite force, how is that possible? How does that nail get driven into the wood? How do you think? Because if they're equal and opposite, shouldn't they cancel each other out? Yes.
Because the nail has nothing to push up against, especially against the wood. So.
Exactly. Because there's also going to be the tip of the nail and its interaction with the wood that it's being driven into. Okay? And so there's a thing called like a force potential. Okay? It's where eventually enough force is applied, an object's going to give. Okay? That wood, you're going to notice that if you've ever tried to hammer nails into various types of wood, some are easier than others. Okay? Some take more force, some take less force. But the action-reaction between the hammer and the nail is a completely different interaction than the nail and the wood. So that's why we are able to still get this net force in this scenario and have the nail driven into the wood. Because that would be awful if you went to go hammer a nail and it just goes boom like the old cartoons did and the whole body's shaken because of Newton's third law. But remember, just because two objects are interacting does not mean there's nothing else interacting. Okay? Quite often there are multiple action-reaction forces taking place in a single scenario, and eventually one of them is going to overcome the other. We're going to skip that one, actually. I want to get going on to the problem. So, we're going to put Newton's second law into practice here. So we have Roberto and Laura. They're studying across from each other at a wide table. Laura slides a 2.2 kilogram book towards Roberto. If the net force acting on the book is 1.6 newtons to the right, what is the book's acceleration? All right. So let's take a look at this. So we're going to be getting some mathing going on here. So I want you to have your calculators handy. All right. Okie dokie. Let's see if, oh dear Lord. Okay. So, what do we know? We know that the book is a mass of 2.2 kilograms. And we know that the net force is going to be 1.6 newtons to the right. I'm just going to use an arrow here. Okay? What we don't know is the acceleration. So we're kind of getting back to a little simpler roots here. So if we have Force equals mass times acceleration. What do I need to do again to solve for acceleration? How do I get this by itself? Divide by mass. So I'm going to get acceleration is equal to the sum of the forces divided by the mass. And so then you get to simply go ahead and do your mathin'. So what do we get for the acceleration? And don't forget that acceleration is a vector. And so we were told which direction that it is going in. So how can I finish off this answer, this label? To the right. Okay? Difficult, eh? Well, that's kind of what you're going to see, but we're not done yet. There is one that I want to bring to the table that I think would be good for us to go over. Okay? So I want you to open up your books to page 132. Ladies and gentlemen, we will have a singer before Thanksgiving. All right. Get page 1. Oh, that's right. Wait, you won't be here. So we have to do it next Friday. Okay. 132. Let's look at number 5. So, Mr. I forgot my book. Go ahead and read number 5. Loudly.
Number 5 loudly on 132.
On page 132.
All right.
Those at home can open their own books and read this themselves. This is purely for the class.
All right. A 2-kilogram otter shows from rest at the top of a muddy incline, 85 centimeters long, and slides down to the bottom in 0.50 seconds. What net force acts on the otter along the incline?
All right. So let's first of all, I like this problem because I get to draw what's happening. Okay. So we've got this incline, right? We've got an otter. I think this is what an otter looks like. They got big bellies and a smile. Okay. I think they have a tail. Okay. So that is the otter of your nightmares. So anyway, what do we know? We know that the otter has a mass of 2 kilograms. We know that it slid down a distance of 85 centimeters. So it traveled 85 centimeters. But do we ever really use centimeters in describing motion a lot of times? What do we typically use? Meters, right? So what is 85 centimeters in meters? 0.85 meters. Again, you just take centimeters divided by 100. All right, and we know the other bit of information is that it took 0.5 seconds. And we really need to figure out, what did it say? We need to figure out the net force. Is that what it was? Okay. So if we need to know the net force, okay, what bits of information are we missing? Acceleration. Okay, we don't know anything. But what we do know is our displacement, really, as well as our time. So we need to go back to chapter 2 and find an equation that matches everything that we have. Okay? And that equation is this. Delta x is equal to 1/2 a times delta t squared. Because it has the variables that we have. it's got displacement, it's got time, and it's got acceleration. So we can figure it out. We can figure out acceleration. So we need to rearrange this to solve for acceleration. And so we get 2 delta x over delta t squared. So now we got it arranged how we need it. We can go ahead and plug in our numbers. And our time was 0.50 seconds. So what do we get for our acceleration? Go ahead and calculate that. Say that again. 6.8 meters per second squared. So now that we have our acceleration, we can go ahead and answer this problem. Okay. So now we have our mass of 2.0 kilograms and our acceleration of 6.8 meters per second squared. So what is our overall force? Say 13.6? 13.6 newtons. Okay? All right. Questions on that? So I'm going to pass out your homework, then I'm going to tell you which ones we're going to be doing. All right, so the numbers I'm going to give you, I want you to circle, and the circled ones are the ones that you are to do. Circle number 1, number 2, 4, 6, 7. Again, circle 1, 2, 4, 6, 7. And that is all for today. So hopefully those of you at home paid attention. Yes? If you are in school, turn it into class. If you are online, submit it to Classroom.